It's actually like unbelievably simple. Like it's kind of crazy that people didn't find it. So you take linear. So here's the map. You take linear polynomials and quadratic polynomials. So that's a one-dimensional space times a two-dimensional space, and you multiply them. So that's a map from a three-dimensional space to a three-dimensional space. So, and then inside of that, you delete some stuff from those spaces, and then that's the example. So it basically is just the multiplication map, and you have to delete you delete some things, for example, to make the derivative injective. So you delete the locus where it's not injective, and that's it. So really extremely simple.
Welcome to Begin Proof. I'm Slater, partner at Bain Capital Ventures, and today I'm talking with Daniel Litt. Daniel is a mathematician at the University of Toronto, where he works in arithmetic geometry. And today we'll be talking about AI-assisted mathematics from the point of view of a mathematician who's working at the research frontier. Well, Daniel, it's been sort of a big news week in math.
Yeah, indeed.
So for the audience, or however I'll say this, is we're recording this after the rest of the podcast that Daniel and I did before, because of the update of the Jacobian conjecture falling earlier this week. So, Daniel, I'm really excited to get your reaction to that. I thought one fun way of opening this would be kind of like, let's put the veil of ignorance back on and say, sort of before knowing that this counterexample existed, what were sort of both sides of the intuition? Like, why would you have intuition that this might be true on one hand? Like, what are sort of the reasons why something like this might be the case? And then, also maybe why you might have some intuitions that it's false. Like, what were, some reasons why it wasn't sort of like totally clear?
Yeah, that's a good question. Yeah, so I think first of all, I tried to. So this is in my area. It's like a conjecture in algebraic geometry. I definitely knew about the conjecture. I would say it's not like my style. I maybe spent a few minutes thinking about it and didn't get anywhere for the course of my career. There's been a lot of work on it, so it's definitely not an attention bottlenecked conjecture. My sense is that there was no consensus about its truth value. It's the main reason for believing it to be true, I think, is probably just that no one had found a counterexample over a long time. So it's kind of anthropological. There's better evidence in the case of polynomials in two variables. So there it's known up to degree about 100 something. And the new counterexample doesn't actually disprove that case. So you can actually, if you go back, if you just search the literature, which I did after the conjecture was resolved, like you can find a lot of people saying there's very strong evidence in dimension 2. Who knows what happens in dimension 3 and higher? And indeed, it turns out there's a counterexample in dimension 3 and higher. Yeah, so I think the reason to believe it's true was basically just no one had found a counterexample. The reason to believe it's false is like there's just no reason for it to be true. It's kind of, no, it's one of these things which I think is like sort of an isolated conjecture in algebraic geometry. Like it's not part of a big program that. Sometimes you can get evidence for a conjecture, like the Riemann hypothesis or something. Like I'm very confident it's true because it fits into this like really complicated and very self-consistent picture that makes a lot of predictions, and many of those predictions have been verified. The Jacobian conjecture, it actually was known to be like equivalent to or like follow from a bunch of other conjectures in different areas. So another reason it's nice to have it resolved is like that resolves a bunch of those conjectures. But it's sort of yeah, I know it doesn't fit into a program. So I think maybe post hoc it was kind of hard to get evidence for it or against it.
Yeah, that's the kind of thing I was wondering like about. So for example, I had a friend who worked on like discrete harmonic analysis, and there's sort of all of these known results and sort of normal continuous harmonic analysis, and like that would give you some intuitions that like the discrete versions like maybe should be true, and but also there's unique features of the discrete case, and like that would also give you some intuitions about like why some things should be false. Of course, you actually have to come up with an argument.
That's actually a really good point. So in fact, there are versions of the Jacobian conjecture that were known to be false. And my understanding, I mean, this is not something I'm really an expert in, but my understanding is that the counterexample Fable produced is like kind of closely related to a counterexample someone else, Vitushkin, I think, had produced to a variant of the conjecture. We haven't seen the chain of thought or the chat session or whatever, so we don't really know whether it relied on those ideas. But yeah, I think you could try to get evidence that it was false by looking at these sort of related conjectures that do appear to be false or are known to be false.
What is your intuition for the proof? So, as you already alluded to, the original tweet was sort of, very playfully cryptic. You could verify these polynomials, sort of have the desired property, but then, you don't sort of have intuition for that. And I think a couple of explanations have come out now. Terry Tao had this kind of analysis flavored one. Somebody else on Twitter, I think it was Andy Zhang.
Yeah,
Yeah.
gave the polynomials to ChatGPT and it like found a pretty nice geometric description.
Yeah. What's your intuition for it? Like now, as you understand it now, like what sort of is your intuition?
It's actually like unbelievably simple. Like it's kind of crazy that people didn't find it. So you take linear. So here's the map. You take linear polynomials and quadratic polynomials. So that's a one-dimensional space times a two-dimensional space, and you multiply them. So that's a map from a three-dimensional space to a three-dimensional space. So and then inside of that, you delete some stuff from those spaces, and then that's the example. So it basically is just the multiplication map, and you have to delete you delete some things, for example, to make the derivative injective. So you delete the locus where it's not injective, and that's it. So really extremely simple. Why it works? I mean, I don't know. It works because you check it works. So it's not totally clear like how you would come up with it if you like decided, well, I'm going to sit down and disprove the Jacobian conjecture. I think that's still a bit of a mystery to me. But I don't know. Maybe you just try a lot of things. It's kind of crazy to me. Like this is a map that has like probably a million pages written about it. It's definitely like a very well-known object in math in algebraic geometry. We like did not discover it because of this proof. It's kind of crazy to me that like no one noticed that there's a counterexample to the Jacobian conjecture sitting right there. But yeah, so I would say post hoc there's a very like quite beautiful and simple geometric explanation for why it gives a counterexample to the Jacobian conjecture. Somehow the only not totally obvious thing from what I said, it like once you know what to delete, is like why so there's a source and target of the map. They're both isomorphic to just F1 space C3. It's not sort of totally obvious why the source is isomorphic to C3. It's sort of an exotic isomorphism. But it's like if someone tells you what I just said, like they're going to finish you're going to finish the proof in like a few minutes probably. So.
Yeah, I wanted to ask about that specifically. So, there's this style of blog post that sort of like you could have invented X. Like Gwern has this interesting thing of like you could have invented transformers, and it's sort of a just so story where if you had the right ideas at the right time, you could sort of follow these logical steps. And I was reading, Andy's argument, and I'm like, okay, I can imagine considering this map. That makes sense. And then I can imagine saying, yeah, I've sort of got to delete the places where it's singular. That's okay. And then the sort of thing is okay. So
you delete a hyperplane tangent to, but not osculating to the small diagonal.
Yeah, you sort of like choose the hyperplane, sort of carefully, and like I guess once you've had that intuition, it's clear that like the target space is going to be A3, or like that's not that crazy. But it's sort of the thing that I have like zero intuition for is like you can choose it in a careful way where the pre-image is A3 too. And like maybe to me that's the part where I have like the least intuition for why this should work.
Yeah, that's also the part. Like I don't know how to tell a just so story there. I think so. One way you might have come up with it is look at this prior Petrushkin counterexample and like try to massage it in some way. Like I wouldn't be surprised if that's what happened. But yeah, I don't have a just so story there. I mean, I think that it also could just be like you fiddle around with that map, and it's a map whose target is P3, so it's very easy to arrange that by deleting something you get F1 space, and then you just fiddle around until you win. I mean, one nice thing about the models is they have a lot of time, they have a lot of energy to just try stuff. So yeah, I don't know. It would be interesting to know like what number thing this was that Fable tried. Was like the 1,000th thing it tried, or the third thing.
Yeah, or even kind of like the edit path of like, you try out a few things, but what are you sort of trying to fix about, sort of the early trials to get to this one? Why do you?
But yeah, I would love to do a story like that. I don't know.
Yeah, I'd be really interested in that too. Why do you think that this was missed for so long? I think that this proof would have been totally. I think this problem was posed in 1844. There's no modern machinery to this argument. You could have people would have understood the proof if it was presented next week. Why do you think it took so long to find this counterexample?
Yeah, it's really a mystery. I mean, I think the history. So in 1844, someone asked about the two variable version, and then in 1939, it was asked about by Gauss, maybe in all dimensions, and then the sort of general conjecture was popularized by Abyankar. But I think again mostly about the two variable version. So I think one possibility is that just most work was happening in the case of two variables. Um, I think another possibility is that the people who were motivated to work on the conjecture believed it was true, even if there wasn't sort of a broad consensus in the community it was true. But I know, I think it's just, my feeling actually having seen this is that probably there are a lot of conjectures out there which just have simple counterexamples or proofs, and we just miss them because we don't do exhaustive search. Like a lot of the way mathematicians work is not like you pick some conjecture and then you like just like work on that and work on that and work on that. Like sometimes that happens. Like you get obsessed with a problem and you just try to go deep on it. But a lot of the time it sort of goes the other way. You have an idea and then you apply the idea and sort of you work opportunistically. And so I'm a little surprised that like opportunistically someone didn't find like literally this counterexample. But that's there's a lot of randomness to like what ideas people have and how they kind of discover that they can apply them. So it could just be that we're very bad at like we search on some very like some Brownian motion in a very high dimensional space, and that means we miss a lot of stuff. And my expectation actually is the models are also doing some Brownian motion in a very high dimensional space of proofs, and they're also missing a lot of stuff. So even probably very simple stuff.
Okay, I think it's interesting that this example and the prior one that we talked about, the Erudition distance problem, sort of the models have succeeded by finding counterexamples, if you will. They're like constructions, that humans didn't. And of course, the models are going to get better in all sorts of ways. We shouldn't expect them to sort of stop here. But, maybe at this point in time, they're sort of like counterexample generating machines. They're extremely good at this. And my question for you is, does that change the way that you personally do research, where it's like, hey, I think this thing might be true. Let's just, sort of let a frontier model crank for a while to, exhaustively look for counterexamples. I'm curious if, the kind of counterexample generating machine, sort of as a distinct thing, if that's changed your sort of research practice at all.
Yeah, for sure. Yeah, I mean, so definitely, like literally any time I have, of course, when you try to prove something, you come up with some intermediate sequence of conjectures and you try to verify them. Like you try to find a path and then move forward on the path. And like definitely when I'm doing this now, like if one of these conjectures seems like it's something that like you could imagine writing down an explicit counterexample, I of course ask the models and of course try to find a counterexample myself. Um, I also actually have like picked up a bunch of projects now where this kind of like having this ability is useful, right? So like sometimes you would like to make a construction, and like the way to do that is like you try 1,000 things, and previously I would have had to try 1,000 things in like serially one after another, and now you can try 1,000 things in parallel. Like the models actually are still in the precise area of mathematics I've worked on, like they're not so reliable like working out examples like this, even the best models, although it's getting way better very quickly. But yeah, even an 80% success rate, if you try 1,000 things, it's actually kind of you get information. So yeah, I think now there are kind of there's a style of research which I think has not existed until now, where like the nature of this trial is you like come up with 1,000 ideas for how to make something, and then you ask the models to pursue those ideas. And yeah, so that's something I've been like trying to do like as an experiment to get the models to do something that I find more interesting.
Any other belief updates from this where, sort of like your predictions or timelines or really like anything that you're betting on about sort of, AI assisted math has changed, sort of on the other side of this?
I think that I haven't really updated on capabilities. What I have, it's definitely updated me on how much we're missing. like I think the big open question for me about the near term impact of AI on math has just been like how much low hanging fruit is there? Like how much can you do without like introducing a big new idea? I'm not saying that the models like will not introduce big new ideas eventually, but they're not doing so now. Like right now, what they're doing is like using known techniques effectively. And my sense had been like probably like attention bottleneck questions were not in general accessible to like known techniques with no big new idea. And I think that's just like wrong. Like I think the Jacobian conjecture seems like very strong evidence that actually there's like a lot of well-known questions where like maybe even you don't need like 20th century mathematics to resolve them. Like maybe it's fine. Maybe there's a lot of interesting open questions that you can find a counterexample to using like ideas from the 19th century. So I think that tells me that I think in retrospect that like should have maybe been more obvious, right? There's just like not that many mathematicians and there's like a lot of problems. But yeah, that's been the big update for me.
I'm not asking you to give any scoops on your current research or things that you're actively working on. So maybe ruling that aside, are there any sort of problems where you think, oh man, this is the sort of thing that you ought to take this approach for, where somebody who knows what they're doing should be rooting around for counterexamples now, or even just like sort of areas if you don't want to name specific problems.
Uh, yeah, that's a good question. I mean, of course, I've been thinking about this. Um, I mean, I should say, I think the areas I tend to work in, I mean, of course, I could be wrong about this, but like I tend to work like adjacent to some big program where we like have, in some sense, a lot of evidence conjecture is true. So yeah, the sort of things that I have been trying to get the models to do is, I guess, make positive constructions, so not just counterexamples. So I don't know. I can give an example. You said I'm happy to say one thing I'm working on, which is there's a sort of mystery in the theory of Shimura varieties, which is some algebra geometric object where they carry what are called tautological local systems, and they're predicted to be motivic. And okay, there's some class of Shimura varieties called exceptional Shimura varieties where we don't know this is true. So I've been trying to, see if I can prove this. This is definitely something like where I do not expect a model to be able to one-shot the answer. That would be like remarkable. But they're very helpful. So you try to make some construction and test it. It has a bunch of properties, and that's something that Codex is now able to do. Like you can you make some algebra geometric construction. You ask it to do a computation about it, and it will succeed. And yeah, so that's something that I've been trying to get the models to do. There's another. I actually find a bit more exciting than the Jacobian conjecture. So there's Akil Matthew got I think Fable to find a counterexample to an old conjecture of Grothendieck about finite flat group schemes. The conjecture was that a finite flat group scheme of order n is annihilated by n. So this is like analogous to the fact that if you have a group of order n, every element has order dividing n. And so there's now a counterexample to that old question. This is something, again, that definitely a lot of people worked on. I think the broad belief was that it was true. So it's maybe the negative direction might have been attention bottlenecked. Then there it seems like there's maybe actually quite a bit to learn about finite flat group schemes from the counterexample. And yeah, I think there's like my expectation is that there's like a bunch of old conjectures in commutative algebra that probably will find counterexamples soon too of this nature, where just like the general belief was wrong. So yeah, my instinct is to look in places where, the field is maybe a bit more technical. I mean, of course, you see a lot of now counterexamples on social media to random conjectures and graph theory that no one has ever thought about before. But yeah, I think there's probably, in a technical area, there's a lot of sort of maybe even guiding conjectures, but if there's only 10 people in the area, the conjecture can be kind of important in some way, but like definitely, the counterexample space will not have been exhaustively searched.
There's one last thing I wanted to ask you about, which is I'm blanking on who it was right now. I was trying to look it up, but someone was making the argument that maybe the Collatz conjecture, we'll get a counterexample to, and they sort of had.
I think Alex Monroe.
That's right.
Was talking about.
Yeah, recognizing it's outside of your area. What do you think about that?
I don't know. I think that's yeah. I have no strong opinion. I mean, of course, that's a case where finding a counterexample would really probably require some quite serious new ideas. So uh, it might be true, but I would be a bit surprised to see a model generate a counterexample conjecture like that. Let's say this year. Who knows what will happen next year? Um, yeah, I mean, I think, but again, I could be wrong. Of course, you hear the premise is that the class conjecture is like well studied enough that like the sort of known techniques have been exhausted. It's not totally clear that's true, but maybe, yeah, my instinct is it's probably true for class in a way that it might not have been true for the Jacobian conjecture.
Yeah, I found his argument kind of interesting. It's like, sort of running it through it, we should, sort of think as like some type of Turing computation. And, yeah, it's sort of an interesting idea I hadn't seen before, but we will see.
Yeah.
Um,
Yeah, and one related thing is there's a bunch of conjectures that are known to be undecidable because sort of the process that is being studied is Turing complete. So sort of deciding the conjecture is like solving the whole problem. And it's also possible that that's true for class. I think that's some mathematicians believe. I'm pretty agnostic about class. I don't know. I do think it is possible. One thing about the class conjecture is that it is definitely something where I think most people probably believe it's true, and maybe that's another place one should be looking for counterexamples. Like, I don't know. My sense post Jacobian conjecture is that like there's some weird anthropological effect where the people working on a problem are like the one, like, why do you work on a problem? You get obsessed with it and like you have to be excited about it. And it's way more exciting to prove something is true than proving it's false. I don't know. And so maybe like we systematically are missing counterexamples just because the people who work on a problem like are trying to prove it. Like they're excited to prove it, not to disprove it.
yeah. Yeah, I mean, it feels in some ways some counterexamples, do a lot of theory developing to create. But, in some case, and maybe the Erdős unit distance one is an interesting example of that, where like, I don't know how you would do.
Yeah, certainly more like that.
Exactly.
Than
but sometimes it just feels like, I mean, there's that famous paper where it's like, a theorem of I forget who it was, but it's like there was this theorem. Here's a counterexample. It's like a one line, paper or something like that.
It might have maybe the Euler sum of powers conjecture. Yeah, so there's like this was sort of very early on in the impact of computers on mathematics. Like someone just like checked up to I don't know the number 100 or something, and they have a one-page paper where they have some sum of powers of three-digit numbers is some other. So I mean, it's an amazing thing. I think it's we're sort of seeing this happen again now. Like we now have a new technology like the computer, and it can now knock out a bunch of these conjectures.
Yeah, I vaguely remember something like this with Mersenne too, where it was like he had some conjecture, and like literally the next one after he stopped was like the counterexample.
Yeah.
Amazing. Well, Daniel, thanks so much for doing this. It was really great to get your reaction to this news.
Yeah, and thanks for having me back. All right, anyway,
amazing.
Talk to you.
Thank you. So, Daniel, thanks so much for joining us.
Yeah, my pleasure. Yeah, thanks for the invitation. It's nice to be here.
What do you think about the aesthetics of the models? And what I mean by that is, at least in my experience, like mathematicians all have kind of, you could prove the same thing in like 10 different ways, and some of those proofs feel elegant and beautiful and sort of, right with a capital R, and some of them feel like a grind or sort of definition pushing, and maybe you get less insight out of them. How would you rate the models on aesthetics?
Yeah, so first of all, I'm actually kind of anti-aesthetics in mathematics. Okay. Like I tell my students that anything true is beautiful, and you should, prove what you're trying to prove by any means necessary. Actually, and I think the models have kind of a similar philosophy. Like they're very happy to grind. Like one way in which the models are superhuman is they don't get tired. And I think that's actually, you can see that kind of reflected in this unit distance problem solution. Like they're willing to try something that I think would, to a human mathematician, like throw up some red flags as like, I can probably get lost in the weeds here. I'm not saying that a human couldn't come up with this. I actually think like if you ask the right human to try to produce a similar argument, it's quite possible they would. But yeah, it's definitely like kind of a scary, like you have to be willing to grind to pursue this kind of argument. and one strength there is like you can see if you ask them to construct an example of something, they're like willing to try 100 things. And that's something very expensive for a human mathematician to try 100 things, like in terms of time devoted to the problem. In terms of like the actual arguments they produce, like are they different in some aesthetic way from a human? I actually think the reasoning the models show, like you can read the summarized chain of thought from the solution to this unit distance problem, and much more summarized chain of thought from ChatGPT Pro when you ask it a math question. It's different from people in that like they will try more things or maybe be more computational. Like they're very quick to write code to do some computation, but the reasoning overall seems pretty human-like. Like I actually don't think there's a huge aesthetic difference. One thing that is true is that the models, I think, generally show poor research taste compared to a human mathematician. I'm not saying this is anything intrinsic or won't change in the future, but it's just how things are now. So, like, for example, I have some project now where I'm trying to produce some construction, and this involves trying like 1,000 things where it's satisfying some numerical parameters and see what happens. It's something where the models are now very useful for. Like, you could just have them try 1,000 things. But yeah, when it comes to, when something doesn't quite work and then you want to repair it in some way, they will often choose some kind of approach to the repair that like has no chance of working, or that it's like purely computational with no kind of conceptual reason to think it would work. And this is something where, I think it's kind of a blocker for them to currently do high quality research in this kind of thing. So that's arguably an aesthetic flaw or something.
How would you, I guess, what would you want to see to feel like they had better research taste? Would it be, sort of 10 different, ways that you could go about trying to, prove some bound or something like that? They're sort of choosing the one that's more likely to work, or how do you eval that?
Yeah, something like that, like just some kind of first principles thinking. And in fact, you can just you can already substantially improve research taste by saying, think about this from first principles often. So I mean, I think one reason why people have research taste is because we have kind of very limited attention and limited ability to compute or spend 1,000 hours on something. Like, we need something to guide us, and maybe the models need that less. So it's also possible that they like start doing high quality research without having research taste, just by doing like a lot more research. I think the way I would measure it is like just seeing, are they kind of understanding the big picture in some way? There's some areas where the models, I think, are like some areas of mathematics, where I think the models are starting to have some kind of big picture view and like able to do some philosophy about the underlying problem. But it's definitely something where there are areas where they're very weak.
Yeah, I wondered about that, sort of implicitly, like humans have to do a lot of compression, right? Like I'm not, it's if it's not clear that this like has some like likelihood of going somewhere, it's hard to sit down and just like try for 8 hours to prove something that you're not very optimistic about working. Like there has to be some hint of an idea that it's going to work. And, I don't know whether it's like a strength or the weakness of the models. You can imagine them finding all sorts of proofs that just like a human wouldn't go down that path because the first, hour of work feels like a blind alley.
Right. I mean, there's one way I think about it is like humans have some bundle of skills, and like, good mathematicians have all of these skills, to some extent, but, typically they're below some minimum bar in like every one of these skills in a bundle. I think that if you were like really superhuman in some of these skills, like technical ability and just like, willing to work for, 100,000 hours straight on a problem, you could probably substitute that for a lot of the other skills. So one way I can see the models becoming like superhuman in some mathematical research tasks is just by becoming like extremely good technically and having a lot of like attention, without having maybe some more kind of big picture philosophical view of a subject. Like maybe you can substitute some other skills for that.
So just on a sort of philosophical point that you made in that companion piece for the unit distance problem, where you talk about how attention starved, sort of some areas of frontier math are. And I guess the way that I think about that is just that, there's not that many humans sort of working in these areas. You have to be very intelligent. You have to go, even within math, it's very fragmented, right? So somebody at the frontier in combinatorics and somebody at the frontier in arithmetic geometry, it's hard for either of them to contribute to the other's, sort of work, so to speak. And so you could end up in this world where it's literally true that on, sort of important problems, there's only like 10 people, sort of working on them.
Yeah, I think that's true of almost every important problem, actually, that probably the number of people devoting serious attention to it is like single digits.
Yeah, and I guess so one thing you could imagine is just that now we have attention on tap. If you're willing to sort of fund the token budget, you could, sort of take that from, hours of human math equivalent and multiply it by 1,000. And I guess my question is like, what do you think that does to like the landscape of unsolved problems? Areas where you're more or less optimistic.
Yeah, so I definitely think there's some problems where all that's missing is attention. So I actually think, in some sense, the unit distance problem arguably has that flavor. Like, it's definitely true that it was not like totally attention-starved. Like, a lot of people cared about it. People definitely tried. But what's true is it seems like people who had the right bundle of knowledge, and there are a lot of people who had that bundle of knowledge, were not trying it. And so I think there's plausibly like a lot of problems of that flavor, where if the right person looked at them and spent a week or two on them, they would be resolved. A lot, like what does a lot mean? I don't think the Riemann hypothesis has this flavor. I don't think the Hodge conjecture has this flavor. Like, I think there are problems where we really do understand well the obstruction to solving them, and like something has to be overcome, and existing techniques just cannot approach that. So for attention to be valuable there, that attention also has to come with sort of ideas that are sort of new ideas that are being produced at the level where we don't really see the models producing them yet. I think the primary way just attention helps is like a lot of the times maybe what we believe is true, like maybe we think you need some new idea to prove something. Well, what if that thing is just false? Right, and then maybe there's there's no actual obstruction to disproving it. Like we've not exhausted a search for counterexamples. So the unit distance problem is of this nature, and I think actually a lot of the examples of after the unit distance problem somehow this idea of using class field towers, which is sort of somehow the technique that the OpenAI's internal model brought to the problem, like resolved a bunch of questions in sort of related areas, like sort of areas of number theory or combinatorial geometry. It's something where, once you have attention put on this idea, you just suddenly start knocking them over. There's a question as to like how many problems have this flavor, like how many problems are accessible to like a short, quick counterexample or something like that once you have the right idea. My sense is that like of well-known problems, it's probably the ones where we have a wrong belief about the truth value of the problem, or where like the wrong like people were looking at them. So like the idea comes from somewhere outside the field. My sense is that like this is like a change in the structure of mathematics, and that like we know a few more true statements, but like it doesn't somehow change the primary activity of mathematicians. So maybe let me give you an example with the unit distance problem. So the unit distance problem, there's something you want to bound, so the number of unit distances between endpoints in the plane. Erdős had some construction, and he conjectured it was best possible. So that construction gives a lower bound on this number, and then there was an upper bound, which was much higher. And most of the activity in mathematics went to decreasing the upper bound. And then what this OpenAI construction did was show that the lower bound that Erdős had come up with could be improved. Okay, so like, how does that actually change the landscape? Well, not actually that much, right? Because it's still valuable to try to improve with upper bound. Like, so most of the activity in this area was not wasted. Like, we still actually don't know what the truth is. There's an upper bound and a lower bound, and there's a pretty big gap between them. And well, okay, now we want to improve the lower bound and improve the upper bound. What's true is that we know a little bit more about the truth of the situation. We have a new technique that we've introduced to the area. probably a lot of activity still goes into improving the upper bound. And I actually think this is kind of the typical situation you see when you have a short, clever argument that resolves a problem. Like, it's not the end of the story, and like the other techniques people developed to approach the problem are still useful. So I think what we get probably is an explosion of short, clever solutions to things that were kind of attention starved or where we had some wrong beliefs. And then after that, like, maybe we go into some equilibrium where people just start asking their questions to the AI to get get answers that are accessible to the techniques the AI uses. And beyond that, once you exhaust what existing models can do, yeah, you're back to sort of the old equilibrium where you actually have to think about it and try to discover something the AI can't do.
Yeah, that maybe sort of like areas where you should sort of expect more rapid progress, and sort of one thing I can imagine is that it's sort of by branch of math. So maybe it's easier to make progress in algebraic topology than it is to make progress in analysis, or the reverse. The other thing I can imagine is maybe what you were just touching on, which is that like just some argument types are better. So I could imagine, for instance, that sort of constructive math, where sort of constructing these sort of like very carefully sort of built objects, that might just be an area where the models dominate humans, and there's a lot of arguments that are like that. Anyway, and maybe there's probably 10 other versions of that I could think of, but I'd love to get your sort of nuanced view of like where you think that the models have superpowers relative to humans, because I think that tells us where we should be optimistic about pushing forward fastest.
You mean like right now where the models are
yeah, maybe, but I'm interested in like point and slope, like what you think is true now, and then where you're optimistic about models a year from now.
Sure. Yeah, I like to slice it by just kind of type of mathematical activity rather than argument type or field. I think like there's certain things right now the models are very good if you need to do something using a technique that's already more or less known. They're starting to be able to like recognize if something is like in an obfuscated form already in the literature. That's insanely useful. That's like a huge use case. And then they're also very good at doing like sort of searches over many possible constructions or like many possible arguments where there's a possibility of kind of a victory after attempting one of these things for a few minutes. So they're very good at parallelization. What seems like they're not so good at yet is like sort of what I would call high depth arguments, where you're maybe guided by taste down a quite long path. Like maybe the typical situation is maybe you've kind of recognized an analogy between your situation and something else, but to actually realize that analogy fruitfully, you have to just develop 100 pages of theory, which is like not an uncommon situation in math research. So I think there are areas where like the typical paper is like a few pages long and a clever construction, and it's quite possible that in some ways the models dominate humans in producing those kinds of arguments soon, or maybe already in some cases. What happens to those areas is not so clear. Like maybe what happens is they just become more like other areas of math where where that kind of argument is unusual, right? Like my expectation is that as long as the models are good at some things in math but not good at all mathematical activities, like humans just start to value the activities the models are worse at. So we end up in some equilibrium where like humans in all areas of math are just primarily doing the activities that can't be substituted for yet, as long as such activities exist.
Maybe that sort of leads to this broader question of like mathematical publishing broadly, and I think this is sort of what you're referring to in the sort of Library of Babel analogy, which is that maybe like the cost of producing a new paper has gone down by a lot, so we should expect sort of a lot more, and maybe sort of sorting through those is more difficult than it was in the past. I think there's the story about Landau when he used to get so many proofs for Fermat's last theorem that he would give out these like slips of paper that said thank you, the first error is on this page, and then he'd like some grad student do it. So I guess I love to hear what you think about like what is happening to sort of paper publishing in math. Is the archive getting overwhelmed? sort of how much effort, is sort of going into verifying / reviewing now versus, sort of what it was like in the past. There's a lot of questions embedded in that, but really what I'm trying to ask is, how is like the sort of the norms and landscape around publishing changing?
Yeah, that's a great question. Right. So already like middle of last year, we were starting to see like a bunch of like many papers clearly generated by, uh, you know, frontier models appearing on the archive. Typically, in that case, they were wrong. Like they were produced by, people who didn't have the capability of checking the output. So I think maybe I was counting in like September of last year. I think there were 7 papers put on the archive with Hodge conjecture in the title and abstract. That maybe of them, all but one seemed to be generated by an LLM, and of course they were all wrong. Now, of course, model capabilities have improved a lot, and now you're starting to see a lot of correct papers on the archive, which are produced more or less autonomously by an AI, or maybe checked by a mathematician, maybe not. Um, Typically, these papers are like not so interesting, but a couple of them are a little bit more interesting. Like sometimes they'll answer an open problem that someone left in a paper. An open problem can either be interesting or not, but I would argue, many of these would have been publishable a year ago, say, in respectable journal. Um, I think there's a question as to whether they should have been. Like, what's true is that historically mathematicians have evaluated one another, for whatever promotion or hiring or whatever, based on output, which is not just like number of papers written, but some way of trying to evaluate the quality of those papers, and well, quantity is a quality all its own. So, if you answered an open problem every week 2 years ago, you'd probably get a perfectly good job. Right now I can open up Codex, I can say spin up 5 subagents to go online, find an open problem in algebraic geometry and solve it, and of those 5 attempts, 3 will be successful. So if I wanted to, I could write 5 papers a day that answer open problems and would have been like respectably publishable, or at least publishable in a minimally respectable venue a couple years ago. If I didn't care about correctness, which some of the people doing this definitely don't, I could probably produce 100 papers a day of this nature. Yeah, so definitely like the publication system cannot survive that, and to be honest, it shouldn't. Like, what we're seeing is, an immense amount of stress being placed on, well, all our institutions, but in particular the institution of academic mathematics, and places where it was flawed are the first places to crack, right? So, right, one flaw is that we use kind of imperfect proxies for evaluating quality of work. And well, instead what we should be doing is trying to directly get at, how much people are contributing and how much they're understanding. That's really hard. But yeah, my expectation is that the journal system cannot survive in its current form. There's just like no way. To be fair, that's not totally due to AI. Like already, it was very, very hard. The time between submitting a paper and getting it published, even for quite short papers, was very, very long. Like I have a maybe 25-page paper that's been being refereed for the last 3 years, just because it's like extremely time consuming to referee a paper, and a lot of people are producing papers, and so you need a lot of people to read those papers, and that's just a very slow process. So I think this is only accelerating something that was already in progress. Like the incentives towards publication were not being kept up with by the system. But yeah, I think we're going to somehow have to find other proxies for high quality work that are can survive the automation of some high quality work.
Yeah, right. The problems already existed, and we've accelerated the contradictions. And I guess what do you think is the solution to the referee problem specifically? Does verification become much more important? Does the standard is that we just expect sort of formal verification of papers is sort of like a norm? Is it something else entirely? Like, how do you maybe normatively, like, how would you propose solving this problem?
Yeah, it's a good question. I mean, so first of all, like, the purpose of the peer review process is not really verification, in my view. like if that was its purpose, it's doing a pretty bad job of it. Like the primary thing that enforces correctness of mathematical work historically is just like the honesty and diligence of the author. You can imagine a world where we switch to verifying everything in Lean, if or when, I guess, formalization tools or auto formalization tools improve to where that becomes practical. I think that should and will happen. But like the primary purpose of the referee process has not been verification. It's been sorting and serving as a proxy for value. And so the institution of academic mathematics in part exists to provide incentives to produce high quality work, and so one needs a way to identify high quality work and reward it. And I think that's mostly what the referee system has been. I think we can imagine other ways of getting at that. So like already when you hire someone, you don't really just like look at their publication list and count papers or look at the venue. Like that's a really weak signal. And I mean, of course, sometimes that happens, but people who are serious about trying to, maintain norms of high quality science aren't doing that. What instead you do is like solicit letters from people who have actually deeply engaged with the work and try to get serious people to evaluate the quality. And I think we'll have to end up doing a lot more of that, rather than kind of relying on proxies, like, I don't know, the name of the journal your paper is published in. And I think one thing that will also happen is like there's a lot of activities like writing a paper that answers an open problem that will just be like in that abstract form much less rewarded. Like
Right.
what we're going to do is, as long as there are activities where humans are clearly adding a lot of value, like those are the activities we'll be trying to reward.
Yeah.
So maybe if you want something a bit more precisely prescriptive, like I think we're going to have to, well, one thing we could imagine is sort of more public referee reports where you have some sense of like, has someone actually engaged with the content here? Is willing to put their name out there as standing for its value. If you want to understand how useful, like how high quality work is, like you can try to evaluate, like not just, I don't know, did this answer some old open problem, but like is it contributing genuine new ideas? And I think we can find ways to make that more publicly apparent. A lot of this will run into like kind of collegiality norms in the profession. And I think we might end up in a situation a bit more like academic economics, where there's like a bit less collegiality and a little bit more, outward airing of people's evaluations of quality or lack thereof of work.
Interesting. Well, actually, I don't know that very well. Like, how would you describe the cultural difference between mathematics and that area of economics?
Yeah, I mean, my understanding is that economics seminars, for example, are like pretty famously adversarial. Like if someone sees a problem in the work, they'll stand up and say something, and then there will be like a vigorous back and forth. In mathematics, it's like kind of unusual for someone to present like a theorem that is false or like a proof that is wrong. Like people are quite honest and careful by and large, although of course there are exceptions. But I think we might, try to evaluate a bit more publicly, like the quality of work, or like, is this idea really new? I mean, I think right now there are a lot of mathematical labors spent like taking some well-known technique and like applying it in a new case. And that's something, I mean, that's fair. Like that's something that previously required a human expert to do. Like just to understand an existing technique and apply it is something that, most people, do not have the training to do. Now we don't need a person to do that, so maybe we shouldn't reward it anymore. And I think maybe we'll, be a bit more transparent about what work has that flavor of like applying a known technique to a new situation, and what is like genuinely introducing new ideas. And and of course it's also quite possible that soon the models start doing that at rapidly, and that will be less valued too. But as long as there's some aspects of mathematical activity where the models are not dominating us, like probably that's what we'll be pointing to, and we'll need to do that more publicly. Yeah, it's a little hard to speculate on these things without knowing the exact trajectory of model development. That like presumably
What do
depends
you
on where they become skilled.
Totally. What do you think about the prospect of, sort of generating proofs that are true, but maybe not very human optimized? And maybe we'll see much more of that. So, for example, like the famous examples, things like the four-color theorem, or the Kepler sphere packing things where sort of a proof comes out, and I think everybody believes that it's like a valid proof, but maybe sort of there's not some feeling of intuition in the mathematician's head. And one thing I can imagine is seeing much more of this in the future. And here, do you think that's likely? Is that a good thing?
Yeah, okay. I do think it's a good thing. Like, I think any increase in mathematical knowledge we have about like fundamental questions is like obviously a good thing. If it's automated, that's fine. Right. So there's a few ways I think this could happen. So first, you could imagine like auto formalization taking off and doing some kind of training the models to get better at math via some kind of self-play with, formalized mathematics. And then they start producing, I don't know, 10 million line of code, lean proofs of things. That I'm not so worried about. Like, I think that's the sort of thing where you can take that artifact and, I don't know, maybe with help of the models, like extract some comprehensible English language proof and develop some theory. Then there's actually there's a lot of valuable activity to be done there, like where you kind of encapsulate that and digest it for humans. And it's important to do that, right? Like if the model's actually proving an important theorem in that way, it's probably not generative. Like you don't learn the technique until it's more digested. So they're like, I think one way we can measure the value of a result is like how generative are the new ideas that are developed to prove it. And, I think it's fair to say like four-color theorem and Kepler sphere packing conjecture and so on, like the ideas are like not as generative as you might hope. Like, even though they're certainly important and very valuable results. So I think the other way you could imagine this happening is just like a lot more results that look like the four-color theorem or sphere packing, just because like the models are good at coding or maybe willing to work through a million cases that a human isn't willing to work through. That I'm a little less excited about, but it obviously has value. It just means that like maybe we still value a more conceptual argument if one exists. And I think that's already the case. Like there's a lot of results which now have 5 or 10 proofs in the literature, and where we still welcome more results or more proofs of those results, just because like we don't feel like we fully understood the situation. So I think that's also it's quite possible we start to see a lot of kind of proofs that are like proof by grind, and then like math changes because like we know some more things are true, but probably we still try to find human proofs of those, or more human optimized proofs of those results. Like, so I don't know how much that changes the activity of like trying to understand the lay of the land.
Yeah, I think to me, there's this interesting idea of like it's inserting like some new layer of sort of like truth or like likelihood of being true. And so, there's some sort of like famous old conjectures or sort of now theorems where like you can check some results numerically, right? Like you can check lots of n for Fermat's last theorem before we actually have a full proof, and you can be pretty sure that it's true. Or you can look for zeros of the zeta function, and you can be pretty sure that most of the sort of ones are on the right line. But there's maybe this like notion of you might also get to this point where there is a proof by grind that take this out like a couple of years, where there's like I know that there is a 2 million page long, sort of like lean theorem for one of these results. And it's not necessarily human intelligible, but we agree that it's true. But we maybe have, sort of no additional intuition about why it's true. You could imagine like a science fiction scenario where that is like so that happens to a lot of open problems.
Yeah, and for what it's worth, my guess is like that doesn't happen. Like I think the models reason in a pretty human way, and like right now, what they're producing is like, okay, it is actually like when the model writes math, it's like typically way harder to check than when a human writes math for some reason. But like the actual reasoning does seem fairly human. Of course, yeah, as I said, like once you see some kind of formalization or self-play take off, maybe things change. But it seems a little speculative to me.
Yeah.
Also, I mean, honestly, the models are good at reading lean. Like, you can give them a lean proof and ask them to informalize it, and they're very helpful at that. So I'm pretty hopeful that if we get like a 2 million line of code proof of some important theorem that seems to be unintelligible, that we'll be able to informalize it and make something out of it. Like, I actually think that would be a cool new mathematical activity.
Yeah, maybe like the kind of thing I'm thinking of. Well, the kind of thing I'm thinking about is like I remember, this is more like a criticism of my own lack of understanding than a criticism of the proof. But like I remember the first time you sort of saw the proof of the prime number theorem, and it's like this thing is bound by this thing, this thing is bound by this thing, this thing is bound by this thing, and you do that for, like a few pages, and then at the end, you're just like, yeah, okay, I guess that we correctly bounded that. But I didn't the first reading, like I don't have any intuition about like why we're sort of coming up with those functions, or like where does this like sort of bound come from. Like I can imagine it would, I think to never go beyond that would be dissatisfying, I guess is what I'm trying to say.
I agree. Yeah. So for what it's, I love that example, by the way. So for what it's worth, for a long time, I felt that way about analytic number theory. And then, I don't know, near the end of when I was in grad school, I went to grad school with this guy, Maxim Radziwill, who's like a well-known analytic number theorist. And I went to one of his talks, and like I finally, like, he explained it in a way where it all suddenly, like whatever argument he was explaining, it all suddenly made sense. And then a few more times I, asked him to explain arguments in analytic number theory. And there's totally a theory, there's intuition behind every step. And yeah, it's sort of hard to extract, like if you're not raised in that corner of mathematics. But yeah, I think one cool thing about that example is like they write in a way where they're communicating to other analytic number theorists, and maybe they don't have to write down like why you're making some maneuver, but there absolutely is intuition behind each of those maneuvers, and it is something you can extract and explain to like non-specialists in analytic number theory like me. So yeah, I think that's like a perfect example of why I'm hopeful about this kind of thing, because like we already do it like often.
Yeah.
I also produce arguments that are kind of unintelligible to, analysts or analytic number theorists to something, and then like, we talk and we're able to make our arguments intelligible to one another. And yeah, so I mean, it's not clear to me that models would have that capability, like especially if you start training a model by kind of self-play and it's sort of untethered from the history of human mathematics, which is, I think, kind of, if you really want to see a superhuman mathematician, like probably there's going to be some amount of that. They might not have that capacity to explain what they're doing to a person, but I'm still hopeful. Like we'd be able to, like we'd do some hermeneutics and try to figure it out.
Yeah, that's like a whole other area that I was curious for your take on, because beyond being a research mathematician, you also teach math, and as a tool for pedagogy, so I think some of the models are pretty interesting, where sometimes, for example, it's like sure, you can check line by line that this argument in this textbook is correct, but you don't have any intuition about sort of why it might be, and like that's a very natural conversation to have with your favorite frontier model. And, I'm curious, like, I guess what you see with students. I have a few different questions about this, but, maybe sort of the models as a tool for pedagogy, curious if what your thoughts are about that.
And what's definitely true is that the way we teach students has to change. Like, historically, you'd give a lot of like the bulk of assessment would be through homework. I would like to give long take-home exams where you'd have a week to do the problems. You just can't do that anymore just because cheating is so much easier. That said, I think the models can be super useful. So already in my own life, like for some project recently, I needed to learn about hyperkähler geometry, and I basically taught myself what I know using O3. So this was like summer of last year. It was not like a great teacher. It made lots of mistakes. That was kind of valuable actually, because like it,
just like a real professor.
Yeah, exactly. Yeah. Maybe it was made about as many mistakes as I do when I lecture. But that it's actually kind of useful to have some checks to your understanding. So that was very valuable. Like I think that just having a sort of semi-expert available at all times is probably helpful. That said, like it again definitely like undermines existing institutional structures that make people do the work, and like you have to do the work. Like if you want to understand what's going on in some at any level of mathematics, you have to do problem sets. You have to like wrestle with the concepts. You can't just like have someone tell you the answer. Right now, you could imagine a way of interacting with the models, like where they're sort of patient tutors that don't give you the answers, or like are able to set good exercises for you. My sense is it's like pretty difficult to get the models into that mode in a reliable way right now. But yeah, of course, one can imagine scaffolding and improved models that are able to be very useful tutors. And certainly it's like as just a resource in addition to a textbook if it's used responsibly. I think we're starting to see, my sense is that over the last few years, not just because of AI, but for a number of reasons, like COVID, for example, there's a group of students who are mathematically very underprepared, but then the best students, my senses, are better than ever because, they're now accessing all these resources online, now new AI tools. And, so people who are really self-motivated, my hope is that this stuff can be really, really useful for them and like, maybe raise the ceiling on where student performance is.
Yeah, do you, I guess, okay, so this is kind of a complicated question, but basically at sort of the end is, do you think that that divergence, is sort of about to go much wider, where, sort of the difference between the sort of the best students and the median student will get larger and larger? And, maybe like, the historical analogy I might make is that like, median horseback riding ability, probably peaked like 100 years ago, but like elite horseback riding ability has probably never been better. And it's partially because you just don't, you don't need to do it anymore. And I remember in undergrad, like, sometimes you'd have these problem sets that you might legitimately spend like 20 hours on. A lot of learning happens between like, hour 5 and hour 20. You can imagine it being very tempting if you have like a magic machine that will tell you the answer, after 5 hours. It might just be too tempting to sort of not use it. But on the other hand, you also experience like fantastic things. Like I remember, I I sort of feel there's like some subjects that are maybe overly formalized in undergrad. Like I sort of felt this way about Galois theory, for example, where you're like, definition pushing for a lot of it. And, this is a normal, sort of subfield. And, it feels like general topology a little bit. And then I remember reading this book by this guy Edwards that was like, I'm just going to go like redo some Galois theory from like the original, sort of Galois paper. And it's very beautiful. And, you can just like throw that in to Claude or ChatGPT and say like, hey, give me more stuff like this, and it will do it. Basically continue to develop Galois theory in this way. And like it improves your, at least for me, like it improves my understanding a lot because you can get the argument in the form that you might like. Or, the other version of this you can imagine is like teaching intro linear algebra, for instance. Like some students might like the very abstract approach. Others might want to see things, sort of done explicitly with matrix calculations. And you can kind of like get the textbook you want on order is like maybe the way you could describe this. And so, yeah, it's really unclear to me like what it does to the distribution of student outcomes. But one thing I could imagine is that it like increases variance.
Yeah, well, I wonder actually how what you're describing already, I could imagine that not improving the ceiling, like by like one way you develop your understanding is by experiencing frictions and then getting past them. And so reducing frictions could be, I mean, of course it's pleasant, but it might harm your understanding in the long term. As for like I really like this question about like whether the ceiling and the median diverge substantially. It seems to me like kind of a question about how the institutions are structured rather than like AI itself. Like you could imagine a world where whatever universities or high schools or whatever don't adapt at all, and then I think what you're saying is like clearly what happens. Like kids who are motivated to learn the material on their own have all these new resources, and so of course they learn more. Kids who aren't motivated, they're only motivated by the existing institutional structures, which have not adapted to changing technology, and then so they have less motivation. That said, like I kind of think right now we're in a period where there's like all the existing equilibria have been destroyed or are about to be destroyed, and like surely there will be new equilibrium, a new equilibrium. Like, and if we value math education, which I think kind of we probably will, regardless of how capable AI tools will become, we'll redesign our institutions to like create new incentives to actually learn. Like maybe that looks like you have 20 hours a week where you go into a room with no AI and you have to do the problem set there. That's like a pretty different model than existing math education. Although to be honest, like that, when I was a freshman in college, like I definitely was spending 20 hours in a room with no AI doing problem sets, and like if someone made me do that, my experience would not be that different from how it actually was. Um, already we're adapting by like, we can't give take home exams anymore. I don't grade homework for correctness anymore. I just try to give some incentive for actually do it. Um, and yeah, I mean, I think we're already starting to see the equilibrium shift in a way that will hopefully address this to some extent. So my expectation is that we probably end up with a distribution that's like not super different from where we are today, like a distribution of skills, as long as like we continue to devote resources to math education, which like I think probably happens. We need to, I guess, you need to convince funders that math education is valuable. Historically, a big part of that has been, that human capital contributes to scientific development and so on. And like, it's possible that changes as the models become more capable. But like, as long as you're not willing to like completely throw up your hands and like hand over all understanding of science to the AI, like probably, math education, science education, and so on continues to be quite valuable.
Do you think that the technology changes you sort of who will be working at the frontier of math research? You could imagine that a different skill set is the optimal skill set now.
Yeah, it's a good question. I mean, right. So what's definitely true is that it's possible no one will be working at the frontier, right? Like if you imagine capabilities get, surpass humans in all aspects. I think, eventually that probably happens. But maybe let me not speculate on the timescale. In the near term, right, so what happens is like the people working on the frontier are the ones who are adding value. So they're the ones with the capabilities that the AI doesn't have. Right now, I think that is predominantly like professional mathematicians still. Like you still need to contribute to most areas. You kind of need to know what the question means. You need to know what the interesting directions are. There's going to be, I guess you could imagine like prompt engineering or something like that being valuable. Like my sense is that those skills are like, you don't really develop that skill. Like it's something where, once you get to some minimal level, you're already eliciting like close to the best possible performance from the AI. And it's just like not that hard to develop. Yeah. So I think there's, right. So what I was saying before is that you can imagine some situations where, being very good at one thing can substitute for lacking other capabilities. And so what you could imagine is people who would not have been professional mathematicians before because, for example, they lack one of the kind of important bundle of skills that has, historically defined professional mathematics, but now that can be substituted for by an AI. And I think that's really exciting. Like, I think there are a bunch of, there are a lot of people who, for example, might not enjoy sort of like grindy arguments. And so, sometimes you have to grind, sometimes you have to do a long computation, but they might be really excellent at other parts of mathematical research. And like now that the AI can do that grind, can often do things that aren't a grind too, but like, there's, we're closing in on a world where the AI can kind of execute any more or less standard technique, even if it's like lengthy and kind of fiddly. So yeah, I think there's we're close to a world maybe where people who are able to kind of understand the big picture, but maybe not, maybe don't enjoy like doing fiddly technical work for weeks on end, are able to contribute a lot more with mathematics. So I think the primary thing I see happening is like an expansion of who's able to contribute to research mathematics. I'm a little skeptical that there are people who have like all the bundle of skills that are relevant to research mathematics who will no longer be able to contribute because like there's still many of those skills in that bundle where the AI is like kind of weak. But yeah, I think they're, as the models get better and better at some collection of the skills, the people who didn't have those skills before will be able to contribute more, presumably.
Yeah, maybe within that. So, amongst professional mathematicians, there's obviously lots of different kinds. And so maybe, the most famous distinction is like the Gowers, theory builders versus problem solvers. And so, curious if you agree with this, but I kind of interpret what you're saying as like long theory builders, short problem solvers. Maybe that's sharper than you would put it.
Yeah. I don't know. I mean, I think of myself as a problem solver, but like in the course of solving problems, I often build theory. So I actually think of that distinction more about like your motivations than like the style of doing mathematics. Although maybe there are other people who think of it as like, oh, maybe in combinatorics you're a little bit more solving problems without building some kind of overarching theory.
Right. I guess, well, maybe just to frame this as a question, like, you can imagine people that are like maxed out in these different dimensions. So maybe like, Erdős is kind of like maxed out in the problem solving dimension, and someone like Grothendieck is kind of like maxed out in the theory building. And there's this question of like who will contribute more to the frontier of math in the future. And I'd be really curious for your answer to that.
That's a good. Well, okay. Also, there's the question who would contribute more to the frontier of mathematics. 50 years ago, and there I think there was already a substantial difference between Grothendieck and Erdős, which isn't to say that Erdős wasn't doing valuable work, but it's like you can think about the way in which Grothendieck's work was generative versus the way Erdős's work was generative was quite different. So my view is the primary way Erdős's work was generative is that he asked lots of interesting questions. And then the methods he developed, sometimes they were quite useful, like the probabilistic method or whatever. It's very cool, but sometimes maybe less so. Grothendieck built this giant edifice that was very generative and important, but also actually had introduced like certain philosophies and ways of thinking that have been very important, but aren't like quite rigorous mathematics. Right. So where's the AI contributing there? So actually, if you think about those two cases, like the things that Erdős contributed that in my view were generative and the things that Grothendieck contributed that were generative were kind of both areas where the AI is kind of weak right now. Asking sort of generative questions or building some kind of big theory or philosophizing. And of course, it's you could imagine someone who's like exactly good in the dimensions where the AI is good, and probably, their contributions are going to be a lot less valuable now than they would have been 5 years ago. I mean, one example of this is that there are people who are just like very, very good at calculating. In some sense, they're like executing well-known techniques, but like they have a lot of grit or patience, and that can be really valuable. Like probably that will be less valuable in the future. And already we've seen that, like, there were mathematicians hundreds of years ago whose primary contributions were doing tables of integrals or, logarithm tables, and like we definitely don't need that anymore. Maybe we see this as like some kind of continuation of the trend where technology sort of replaces certain human skills and makes others more valuable. And I think like until the models have all mathematical skills at above the level where humans do, that's probably what we see. Like we start just shifting value to the places where they're weaker.
Yeah, as an aside, it's really interesting to me. It's like history of math. It's like really surprising how much people in the past loved calculation. I think like Gauss has this line where he's like, there's no more pleasant way of passing time than sort of like, doing like he would never. I forget what it was, but it was something like I don't remember any of the binomial coefficients because I just like to rederive them each time, or something like that because it's just so pleasant to do. What a nice way to spend 15 minutes, and it does make one wonder. If you didn't, I don't feel that way, and maybe like lots of sort of work. I don't know if you'd agree, but lots of working mathematicians maybe don't feel that way. And there was like this thing where that would have been really important in the past, but is less important now. Maybe sort of one other historical. Oh, sorry, go ahead.
Oh, going back to your question about like, will different people be contributing? Like one thought on this is that like people who are doing like professional mathematicians are like often people who enjoy parts of the activity of doing professional mathematics. So like as those activities change, like you imagine, right? So there are people who enjoy like grinding out big computations. Like maybe fewer of them end up going to math, not just because their capabilities are can be substituted for by technology, but also just because like the other parts of math that are more valuable are less fun to them.
Yeah.
And so one could imagine just different people getting into it just because like you're now doing activities that are fun for different people.
Maybe so one other historical question I wanted to ask you about is, I think people, the trend has been towards specialization over time. I think people describe, I think it's Poincare, people describe as the last generalist in math. Are we entering a new era of the generalist where, the value of being hyper specialized to something, it's not that it's not valuable, but it's sort of less of a barrier to doing good work than it was in the past?
That could be. This is something I've been wondering about, right? So one thing is I do think it's true that mathematicians specialize now more than in the past. That said, I think that there's some sense in which it's less true than one might think, which is like at least there's parts of math where the culture is like we'll use anything we need to use, well, and you're willing to learn, X if you need X to move forward. And then there are people who, while they don't know all of math, have like a pretty broad sense of like what the tools available are and like know like, oh, well, maybe this tool could be useful for the thing I'm working on right now, so I better go learn it. And I think that's possible because it's now like much easier to learn like some far-flung area of math than it was 50 years ago, just because you can now, go online and or there's a lot of books and papers easily available. You can easily contact an expert. There's many more mathematicians, so you can talk to the person you need. If you don't learn it yourself, it's very easy to collaborate, and there's a lot more collaboration now happening than there was even 15 or 20 years ago. So I think there's a culture where like definitely there are some areas that are a little more siloed than others, but like at least in my senses in arithmetic geometry, number theory, like people are willing to learn anything. And yeah, so my hope is that like, well, okay, now we also have a collaborator who's like pretty technically proficient and also in some sense knows everything. Like maybe that accelerates more. Like maybe, sorry, here the collaborator is the AI. So yeah, I think it's possible that, being a generalist in the sense of like knowing everything is like probably impossible and might like, bare knowledge might have like a little less value. Like maybe you kind of do more lookup kind of. But yeah, if it's easier to learn any given topic when you need it, that could increase the amount of generalization, if not the value of having already generalized.
Switching gears, I want to touch briefly on the Millennium problems. And so the question I want to ask is, holding Navier-Stokes aside, if an oracle from the future came and said one of the other problems, some 5 years from now, we have a complete solution that's very satisfying, as satisfying as the Poincare conjecture solution. Which problem would you say that is?
Like which one would I expect to have been solved?
Yeah, exactly. Like if you have like some, it's not like what probability of that happening, but like just if we knew for a fact that one of them got solved and you had to guess which one.
Yeah. Okay, so maybe the ones I'm most familiar with, like meaning I feel like I pretty well understand the landscape, are Riemann hypothesis, Birchman-Swinnerton and Dyer, and Hodge conjecture. Of those, I would, maybe this is going to be controversial, the one I would be least surprised to see solved is the Riemann hypothesis. And I think it's for me that's because I think we have some hints as to what the shape of a proof should look like. Meaning, right? So Deligne proved the Riemann hypothesis for varieties over finite fields. My sense is that, like at the time, actually, people thought like the Riemann hypothesis would come next. Like they thought like the ideas were so like it was kind of clear in some sense like what one would try to do, and like and then that didn't happen. Obviously, like there's clearly a lot of new missing ideas. That said, my sense is like we're starting to see hints about what those ideas are. Like I could kind of imagine, even this sort of expectation holds even if AI is kind of irrelevant to the conversation. Like I think there are ideas in the air right now that like you could imagine kind of leading to a proof of the Riemann hypothesis. Maybe not in 5 years, but like before too long. I think, one comment on this is where you can ask like how long does it take before the last like hint of a big idea and the proof of a major open problem historically, and it's like pretty fast. So if you look at like the proof of Fermat's last theorem, depending on what you can like even sort of the conjecture like the Taniyama-Shimura conjecture was like only 20 something years before the proof of Fermat's last theorem, and that's like the conjecture that gives you the first hint, not let alone the first like major idea, the last major idea rather. The other one I would be somehow less surprised about is P versus NP. And again, I think this is probably going to be a little controversial. My sense there is like we just have no idea of what to do. But you could kind of imagine Right. So maybe the question for each of these things is like, how many big ideas do you need? With Hodge conjecture, like, okay, there I feel like there are like definitely some serious, like a number of serious obstructions to proving it that have to be overcome. With P versus NP, I'm not an expert in the area, but I could imagine that there's only one kind of serious idea needed. And then, okay, the other ones I don't feel confident enough to opine on.
That's awesome. Maybe as an ending question, what will mathematicians be doing 10 years from now? Like, how do you sort of think the field will change? And for people that are actually working on the frontier of new mathematical knowledge, what will the job look like?
Yeah, that's a good question. Right. So I think there's a few different possibilities, like kind of depending on the trajectory of how AI capabilities develop. So, one possibility is that the AI is better than us at everything. And so, if you want to answer a question, like you ask the model and, well, it either succeeds at some, level of inference compute or it gets stuck. So in that world, I think a big part of what we do is like decide what to spend inference compute on. So there are already fields that are in some ways like that. Like, to do astronomy, you need access to a radio telescope, which is or whatever, some kind of optical instrument. It's very expensive and it's limited resource. And so part of what astronomers do is decide how to spend that resource. So if you believe, that questions human mathematicians are interested in are still like primarily what we should be studying, which is I think at least a reasonable belief. Like maybe what we do is decide where to aim kind of our radio telescope. I think this depends a lot on like exactly what the shape of capabilities are. Like, so you could imagine a world in which the AI is like very capable, but like spending $1 million in compute doesn't really buy you much more capability than 1,000. And in that case, I think things are kind of different. In that case, like maybe, well, you ask the AI, it gives you an answer, great, you understand it. It doesn't give you an answer, then maybe you like try to actually do some work at that point. Like, of course, you maybe have the feeling that you're not going to make much progress, but you can still try to understand what the obstruction is and what's missing. So I think that's still a valuable like human activity. Okay, so 10 years out, I think there's a pretty good chance that there are quite a few mathematical capabilities where humans still have advantage. In that case, I think there are a couple worlds you could imagine. So maybe I've described a world A where the AI is better than us at everything. World B is where it's better than us at everything measurable. I think this is like a pretty plausible world because you can like hill climb on anything measurable. But like I think it's quite possible that there are valuable talents, or like skills for doing mathematics that are very hard to measure. And this is also probably true of most other human activity, that there's like valuable skills we have that are hard to measure. So in this world, what you see is like AIs doing all sorts of very high quality research, and then also sometimes, for whatever reason, humans are also proving interesting theorems or discovering interesting phenomena that the AI have not discovered. And we don't really understand why that is. And maybe, it's happening less and less often as time goes on. But in that world, maybe the equilibrium is not so different from where we are today. Like, people are just working on stuff that the AI has gotten stuck on, and sometimes we succeed without exactly understanding why. Okay, then world C, and I actually think this is kind of what the near-term trend looks like, is that AI is more like one or several outstanding mathematicians than like dominating us in everything. Like, so right now there are like mathematicians who are way, way better than me at math, arguably. But I still think somehow, like, even if you imagine they had unlimited attention, like what I would be doing would still be valuable, just because like we have very different predilections and approaches to a problem. So like, to think a problem, I'll take some route that like what another mathematician would never have tried in a million years, just because we're different people. So in that world, like humans are still contributing like cognitive diversity. And yeah, I think this is like kind of what we see with current tools. Like they're starting to be really superhuman in some things, but in a very idiosyncratic way. And so, yeah, I don't know if that lasts 10 years, but I do think it's a possibility.
Awesome. Daniel, thanks so much for doing this. This was a great conversation.
Yeah, my pleasure. Thanks so much for the invitation. It was really nice to chat.